Alright, welcome to Mr. Allen's finite class. Today's video is going to cover section 3.1, which is on trees and equally likely outcomes. This section has the following items in it. We'll talk about something called sample space, the fundamental counting principle, that's kind of the big idea, and something you may or may not have seen before called factorial notation. Let's start with sample space. The sample space is simply the set of all possible outcomes of an experiment. So, for example, consider the following experiment. What would be the sample space for rolling a die? Now, that's pretty much about as easy as I can make it. So the sample space would be the following set. So when we label our sample space, we're going to use set notation. I'm going to make sure that my pen here is working. And okay, good, it is. We're going to do, S equals, and then don't forget to do your curly braces. So we're going to do our curly braces. So when I roll a die, I could get a 1, I could get a 2, I could get a 3, I could get a 4, a 5, or a 6. That would be the sample space for this particular experiment. We could also talk about the cardinal number of this set, which would be the number of items or elements in this set, which would be 6. Let's look at an example. Let's say that I have a die and it's rolled and a coin is flipped. List the outcomes for this experiment. Okay, so let's see here. So that's the sample space. So we're going to have to make a set. We're going to use our set notation again. And my pen's not working here. Oop, there it goes. Try that again. Okay, so we're going to roll a die so I could get a 1. Now, in addition to getting that 1, I have to flip that coin so I could get heads. I could get a 1, and I could get tails. I could get a 2, and then I could get heads. I could get a 2 and tails. I could get a 3 and heads. I could get a 3 and tails. I could get a 4 and heads, and I think you're probably catching on by now. And then we could wrap this up here, a 6 heads and a 6 tails. Okay? So how many things are in the set? Now, it doesn't really ask us that, but we're going to get to that. That's the kind of the point of chapter 3. So how many things do I have in my set here? Well, we can quickly count up here. So there's 4, there's another 4, and there's another 4. So we get 12 items total. 12 items total. Let's talk about a tree diagram. A tree diagram illustrates the different outcomes of an experiment. I'm sure you've done tree diagrams for other classes. Let's look at the tree diagram for the experiment that I just did here. So the first thing that we did is we flipped a coin, and that gave us the numbers 1 through 6. Then the second stage of the experiment was, I said that backwards, didn't I? I'm sorry, the first stage was rolling a die, so you get the numbers 1 through 6. And then the second stage of the experiment was flipping a coin, so you get heads or tails, heads or tails. Now you could actually use, if that previous slide, if you have a hard time like remembering all those things, you could simply list the sample space right here, right next to your tree diagram. So you get 1 heads, 1 tails, 2 heads, etc. Let's look at another example. So now we're going to start talking about cardinality. How many 4-letter codes can be formed with the letters W, X, Y, and Z if each letter can only be used once in the code? Draw a tree diagram. Now I'm going to cheat here a little bit. Instead of writing all of these out, I'm actually going to just have the work pre-written. So let's let's think about this here. So we're going to do 4-letter codes. So there's going to be 4 possible letters we could put in each slot. So think about what that tree diagram might look like. So let's see what it would look like. Okay, so now you can see why I probably didn't want to write that out. So the first stage, or the first number or letter that we're going to put in the code, is either W, X, Y, or Z. So this right here, this first column, is like the first stage. Now, here's the second stage. Notice that this second stage only has 3 numbers, or 3 letters. And the reason is on the question itself, it says that each letter can only be used once. So then when we get to the third stage, we're down to 2, and then when we get down to the fourth stage, there would only be 1 left. So for example, one possible code would be X, W, Z, Y. Notice you only used X once, W once, Z once, and Y once. Okay. Now if I asked you to write the sample space for this, that would be pretty big. And it would be all of these guys over here. It would be all of these. Okay. So how many ways is that total? Well, if we wanted to count these up, 1, 2, 3, and keep going, and you get an answer of, there are 24 ways. 24 ways. Now this isn't a very big example in terms of the numbers. Can you imagine if I made this, you know, a 4-letter code with all 26 letters of the alphabet? I mean, can you imagine how big that tree diagram would be? Let's see if we notice anything, if there's some way we can make this a little bit easier to see what the total number is, or the cardinality. Do you see a pattern? Well, that's where our key principle for this particular section is, which is the fundamental counting principle. Now I'm going to read this and go through it, and then I'll talk about what it means. It says, given an experiment that consists of k stages, in which the first stage can be performed in sub 1 ways, the second stage in sub 2, no matter how the first stage was done. So there's a little bit going on here, and so on. The total of different ways the experiment can be performed is given by the product n sub 1 times n, so the number of things in the first stage, times the number of things in the second stage, times however many stages there are. What the heck does that mean? In layman's terms, it means this. Determine how many ways you can do things in each individual stage, and then multiply them together. In that previous example, we had a 4-digit code, and there were 4 letters that we could pick. Now we could only use each letter once, so there was 4 options in the first stage, 3 options in the second stage. Sorry about that. And then I erased that. That's interesting. And then there was 2 by the time you got to the third stage, and then there's 1 when you get to the fourth and final stage. So 4 times 3 is 12, times 2 is 24, times 1. So this is a quicker way to get the cardinality of our set, the fundamental counting principle. So let's see if we can apply that to another example. How many license plates can be produced using the symbols on each plate where the first 3 symbols are letters of the alphabet, followed by 3 symbols that are numbers selected from the following list? Okay, so we're talking about letters in the alphabet, so how many letters are there in the alphabet? And then we're talking about the numbers in this list, so how many things are in this list? So we got 2 stages here. There's 2 stages to this experiment, basically. Now we got to be careful because we are talking about 6 total slots. So we've got 1, 2, 3. So we're picking the 3 letters of the alphabet, and then we're going to pick 1, 2, 3. So that would be the numbers. I mean, I guess you could argue that, yeah, Mr. Al, maybe that's not a good idea. There's maybe 6 stages. Yeah, there'd be like 6 stages here. So let's see how that would work out, because we got 6 slots to fill. So there are 6 slots to fill. The first 3 are letters from the alphabet. The last 3 come from the 8 elements, those number elements that we have. So how would that work out? So again, let me just repeat. We have got 1, 2, 3, 4, 5, 6 slots. We're going to times these together, and the reason we're timesing these together is because that's what the fundamental counting principle tells us to do. So how many ways could we pick? Remember, this one here is a letter. How many letters could we pick from the alphabet? Oops, we've got 26 here. All right. Now, how many letters do we have to pick from the alphabet here? Well, we still have 26. Now, in the previous example, we saw that we reduced each one of these stages by 1, so you might have thought that this should be a 25. But there was no restriction on the letters. You could use A here, and you could use the letter A here. So there's 26 for this slot, 26 for this slot. Now, over here, we had the 3 numbers, and they were 1 through 8. So there are 8 numbers to pick from here. And again, since there's no restrictions, there are 8 numbers there. So basically, we're going to do 26 times 26 times 26 times 3 times 3 times 3. Another more concise way that you could write this would be 26 to the third times 8 to the third. Now, if you can imagine doing the tree diagram for this, it would be humongous. In fact, it would have almost 9 million items in the sample space. This is exactly why we want to get to this fundamental counting principle, because it's going to help us take care of these really big problems very quickly. All right, factorial notation. You guys have hopefully seen this in factorial. So factorial notation is such, so it's n factorial is equal to n times n minus 1 times n minus 2 dot 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 2 times 1. Well, what the heck does that mean? Well, okay, oh yeah, a couple things we need to know here. 0 factorial is equal to 1. So let's say I wanted to do 7 factorial. Well, if I wanted to do 7 factorial, that would just be 7 times 6 times 5, 4, 3, 2, 1. Times them together, you get 5,040. You might want to pause the video and make sure you know how to use this button on your calculator. Let's look at another example. How many ways can 8 people be seated in a row of 8 seats? So let's look at the solution for this. So we've got 8 people and we've got 8 seats. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Now, how many people could we put in the first seat? Well, you could put 8. Now, we've put one person over here. How many are left? 7. Then there would be 6 left. 5, 4, 3, 2, 1, or what we would call 8 factorial. There's 8 factorial ways to sit them in those seats. Just with 8 people sitting in a row, there are over 40,000 different ways. 40,000 different ways to seat them. Let's look at another example. How many ways can 8 people be seated in 5 seats? Now this problem's a little bit different than the last, because now we were still dealing with 8 people, but we only have 5 seats. This is so basically 3 people are going to not have a seat. So how would that work? So we have 8 people we're picking from. We got 8 people we're picking from, but we only have 5 seats. Let's see here. Here's our solution. Again, this is a problem a little bit different from the last one because we only have 5 seats. We're going to still use our fundamental counting principle. So here would be the work. Now we've only got 5 slots. So, and again, we're going to times because that's what the fundamental counting principle tells us to do. So we have how many people to pick from? I think there was 8. So the first seat we have 8 people to pick from. Now once I've picked that person for that slot, how many people are left? 7, 6, 5, 4, oops, and then this one's 3. Now we've went all the way from 40,000 down to just under 7,000 ways. So we've seen a tremendous decrease in the total number of ways. Please note, this kind of looks like factorial, but it doesn't go all the way. We will see in the next section a more concise way of writing this. That's it. Have a good day.